we know all the, let me record it over here too. One, two, three, yeah. So we know all the tricky stuff about doing parallel processing manually. Like you're learning threads and you understood threads don't return anything. You have to pass references back. If it's common, you need to have mutexes to lock the resource before you want to do something so race conditioning doesn't happen. We examined a few different things, and you saw that how we're going to get into trouble if we actually not do those things. So now, what I'm going to go through, and we found out how to see how many processors we have on a computer so we can have that many things actually doing our tasks. Another thing we need to learn is because that we have, when you are writing a multiprocessor, a parallel processing program, let's say you are on AWS. Who knows what is AWS? Two people? OK. Well, AWS is essentially one of the services that is provided by Amazon. They give you virtual servers. So you go on a website, and I say, I want 8 gigs of RAM, I want 4 CPUs, and I want this operating system, so on and so forth. So it creates a virtual server for you, and you install stuff on it. So say you create a server for your website on AWS, and you have 4 CPUs, and you're doing some search with parallel processing thingy over there, and the website, you have lots of hits now, and you need to make it more powerful. So you simply go on the web, and you say, now I want 8 CPUs and 32 gigs of RAM. And it just, on the cloud, it changes. OK? So your program has to change, too. Now your program is running over there. It used to work on 4 processors. Now it's supposed to work on 16. So that's why you have hardware concurrency. That tells you now it's 16. So you should be able to change the number of threads on the fly when you want to. OK? How do we do that? With vectors. Vectors. OK? So we do it with vectors. So essentially, you can create a vector of threads, as you see over here. OK? You can create a vector of threads, and you can push back threads into it. As soon as you push back a thread into the vector, that's the time it runs. So this is the awful way of showing it, but I wanted to have specifically showing you the code that we have written with several different things, so with a caret and a dash and an underline. So it's the same version of that one, but this one is with threads. So it's with vectors. So I'm actually pushing the threads that I used to create separately and join at the end, 3 of them. I'm pushing them one by one into the vector. As it's being pushed to vector, again, RAII happens, which means it starts executing. OK? Now, whatever I'm supposed to do in it, it's going to happen. But how to join it, I simply go through the thread. One by one, I join it. You see? I say auto T, the thread that I have, and I go T.join. So one by one, all the threads will be joined. And you got to make sure that, referencing is important. OK? So yeah, and that makes your life easier. Now, having something like this, I think I'm on the wrong thing. Copy. Don't save. Yeah, this is for today. Yeah, so let me make sure that oh. Will it run? It ran, because I'm not using anything over here. But I have to set it, because if it's like for example, if you use scoped guard for mutexes, that's C++17. So you have to make sure that you set it to C++. On here, set it to 20, and if you're working on any Linux system, see what the documentation tells you and run it that way. So yeah, so well, this one would be thread vectors, okay? Now, the exact same way, just different examples of the same thing. With functors, remember, no difference. It's the exact same thing. I have a functor now. I'm just passing the functor instance to the thread because it's a callable object. Therefore, it will call it like a method. It doesn't make any difference. But the difference is that when you're passing a functor, you have to make sure you pass it actually by reference. And the exact same process happens and runs and joins. No difference. The only difference is that instead of functions, I have 3 functors over here. And because functors are being called using the call operator, and the operator is returning void, it's suitable for a thread, and it works the exact same way. Are we OK with this? It is extremely easy to learn these things if you go home and actually run these. Me running it over here for you won't do anything for you. I run it over here and say, ooh, beautiful, it's printing stuff. That's not good. You have to actually go home, run it, change it, see how it works, OK? And that's going to just fit in. With mutexes, works the same way. Take a look. In here now, I have the character thingy printing, and I have a scope lock for the mutex that is LG over here, and I'm locking it when I'm doing this, right? So it's the mutex that I had. All I need to do is to create the exact same vector thread that I created. Instead of 3 separate instances of thread, I push them one by one into the vector. OK? And don't worry, as it goes forward, it's going to go easier. We OK with this? Go ahead. What's a mutex? Oops. A mutex is a lock to make sure that the shared properties, the threads. OK, this characters function, it's running in 3 different threads parallel, right? 3 of them are running at the same time. Now, if all of them start changing the value of second, you're going to be in trouble. So that's why you have a mutex called mx over here, OK, that we receive the reference from here. And using scope lock, we lock it. It's exactly like the door of the washrooms that have a lock at the back. You go, you open the door, you can go in. You go in, you lock. Everybody's waiting over there for you to do your business. You finish, you unlock, and you come out. It's not civilized. Everybody runs to the washroom to see who's going to go in first. As soon as the first person goes in and locks, everybody else waits. That's what the scope lock is doing. So essentially, it says, lock that mutex. In its constructor, it locks mx. And when the function is over, it unlocks it. And therefore, OK. Does that make sense? OK. So this is the first example that I gave you with ready go type of thing. Remember that? It's the same thing over here, but the difference is that over here, when I actually do go, you don't know which one is going to run first. It will go in sequence. But again, it's a competition. The first one that gets to the mutex is going to run, and the other 2 will wait. As soon as that comes out, the other 2 are going to compete to see which one's going to go. But whatever happens, it's not going to be a race condition. So this is and that brings us to, I said it's not going to get complicated. This one is complicated, but after that, this is not. This actually makes things much, much simpler and easier. OK. Why multi-threading is so difficult? It's so confusing. It's because you don't know when the function is going to finish its job and return the results that you want. That's the problem with multiprocessing. When you're actually having 5, 10, 20 functions running in parallel and you want to get the results back and do something with it, you don't know when it's going to end. So that's why a mechanism is created in C++ called promise, which essentially you create a promise and tie that promise to its own future. You keep the values in the promise in your functions. So in your function, the value will be updated in the promise. Then you go outside of the scope of that function and refer to the future you tied to the promise. And you get the value back out of that one. So when you make a promise you can get its value in future, which means you don't need to worry about when the function ends. Your future will have the value in it when function have finished its business. Got it? Now, what is the syntax for it? So essentially, so first, I'm not going to put the syntax first. I want you to visualize it. You create a promise. Every promise has a method that generates a future. You extract that future out. Therefore, each promise is tied to one future. You keep the futures when you are where you want your results back. You modify the promises in your threads. When the business is over, you just check your future and you have the value back. And you don't need to worry about, is it joined, it's not joined, when I'm going to get this value. You join it, and after the join is done, in future, the values are going to come out. Good? OK. Now let's see how. It's not actually difficult. I'll show you the code. You're going to see it's a very logical thing. So as you see, I'm creating a couple of promises over here. You see, what I want to do, I want to find the sum of all the numbers from 0 to this number. I cannot even read this number. Can anybody read it for me? 1,235,000,000. OK, so I want to go from 0 to the end and sum up everything. 1 plus 2 plus 3 plus 4. Lots of things to do. Pointless, but it's lots of work to do, right? So what I want to do, I want to divide this by 2, give one half of it to one thread, and the other half to the other thread. One of them will do the sum. The other one will do the sum. When it's finished, I just add those two. I have the total, right? So it's going to be faster. OK? So I create the first sum promise. And I'm going to say the sum future is sum promises get future. This is what I told you. So sum future is tied to sum promise. Then I create sum promise 2. And I'm going to say sum future 2 is sum promise 2's future. Therefore, sum future 2, sum promise 2 are tied together. Sum future and sum promise tied together. Are we good? Then what I will do, I will move my promise into my thread. Make sure it's not copied. I will move my promise into my thread. So I'm going to say my sum, the ULL is just a type def with unsigned long, because this is a huge thing. That's why I made it ULL, so I don't have to write unsigned long, so I say ULL. So I'm going to say create a promise that holds a ULL, OK? And receive it into some promise. That's move reference, right? And sum everything from beginning to the end. So ULL sum, I'll calculate it, and then I'll set the value of some promise to the ULL value that I have at the end. Got it? You OK with this? Again, the exact same type of promise I created, I'm going to put it for my function. I will receive a movement of the same promise into this function. Therefore, this function will have my sum promise in it. Therefore, when it's finished, sum promise gets destroyed. It knows its future should be set. If you don't move it, it's not finished. So you have to move it. Okay? So you move the promise into here, and then you calculate whatever you have to do. You put the result into your promise. Now, the two threads are running. The first one is saying find the sum, right? Oh, sorry. The first one says run the sum, move sum promise 1 from the beginning to n divided by 2. So first half. Then it's going to say run the sum, move the second promise into it from half to the end. We're good down to this point. Now, all I need to do, math is being done. Sum is sum future get plus sum future to get. Done, then I join it. I don't need to worry about when and how it's going to come out. When they're joined, the program's going to get complete. It waits for everything to be done. When it's done, it's going to get executed. And therefore, I'm going to get my sum back. So if I run it, you will see that it goes like, there you go. So that's the sum. Yes?
So promise and future so that we can split the work up? Or is it so that it...
So you can return values back with no collision, no locking, schmocking thingy.
So it's so that we don't have to use mutex?
Yes. Okay. Yes. No, sometimes you still need mutexes because, for example, you want to find out all the things related to a key in a database. Many of them. And then you have a bank of keys that you want to search through it and find several keys out of it. These are two threads. If you just run them, the one that is searching for the key may happen before this. So for that, you may use mutexes to make sure that runs first. When it's finished, then the search is done. You follow? Although with promises, we can fix that too. If you have the future of that promise in the other thread, then that thread waits for it to finish, and then so again, yes and no. You can use them and not use them if you want to. So it's very possible that the mix-up, everything is used. Soon you're going to see that's going to get fixed too with the promise thingy. But anyways, so so that's that for now. So in here's ABCD, promise kept in future. I love the naming. The naming was genius. So this is a time test for the promise and future that we had. So I divided those things by 4, and I'm going to run it. And you got to wait a little for this, I guess. Dun 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 dun. Not the best singer, right? It's doing some calculations. Give it some time. With what?
Like JavaScript's async and like call.
I have no idea how JavaScript works. Sure. Okay, I know JavaScript as an HTML guy. Yeah. I'm not that deep in it. I don't know. Oh, there you go. So as you see the first one finish, the second one, how quickly it went through. So the first one is just doing it as a linear one function. The second one is dividing it by 4 and doing it. You see the difference? Much quicker, right? And that's what parallel processing is, essentially. And this one is done exactly the same way. Some promise 2, 3, 4, okay? But this is like doing it in kindergarten, because I know now that I can put these things in a vector. Why do I have to create 4 of them? You follow what I'm saying? Okay, let me just go through this. So CDE. Promise future time test. So this time test, like depending on how fast your CPU and how powerful your machine is, will change from part to part. But there is one thing, like when I run this using software concurrency at home, I have a Xeon server at home with 32 cores. So when that thing is running it, it's not going to be like this. It's kind of, and this is a very old Alienware, so it's not a very fast machine. So at home, when I wrote that thing, it took 5 seconds. In here, we waited this long. That's the difference between machine and machine. And so it's a good idea to test it on different machines and see how they work. Is that a question, or you're okay? Okay. Now that we learned the future and promise and sum, I am happy to tell you that you don't need to use it. Because there is something called async. Async is exactly like a thread. But the difference is that it returns a value. What it is return? A future. Whereas the promise, you don't care. Promise is made in the sync. So all you need to do over here is essentially create you see over at the future int, and I created F1, F2, F3. Now I have 3 futures over there, and I get them one by one, and it's done. So I don't need to worry about creating promises and the future. So async is exactly like thread, but the difference is that it returns a promise. Okay? And the good thing about it is that with async, you can actually return a value. And what you return in your function is what's going to be the type of the future is. Anything you return in your function, that's the type of your future. See, made it easier, isn't it? Okay, so yeah. So that's async, and that's what's in the notes. Okay? He's laughing over here. I'm so happy. Okay, so that's async. And you can do the exact same thing in a proper way with actually vectors. So you can create a vector of future ints, and you can push back the asyncs to it one by one. And at the end, simply go through the gets of every future and add them up and put it in something. I don't know. You see, I create an array of, why did I do this? Anyways, but sure. I have an array of 3 integers, and one by one, I'm getting the futures out of the vector and put it in here. And that's that. Okay? Then that's probably a sample of what you're going to do in final. A, B, C, D, E, F, G. Async and vectors. Yeah, and this is threads. This is the thread version of doing what we have done using hardware concurrency. So now I'm actually doing that partial. You see, there's a partial sum. It's the same thing that we have done. So in here, I'm instead of a value, I'm going through finding the sum of all the stuff in a vector. So I have, I don't know how many things I have in this vector. I have 100 million ones in this vector, and I want to add them all up. Okay? Again, something stupid, I'm just giving it lots of things to do. So I'm going to say number of threads is equal to hardware concurrency, so I know how many threads I can have. I'm going to have a thread over here. I'm going to have a vector of long logs, which I'm going to hold the partial sums in it, to the number of threads. So if I have 4 CPUs, I create a vector of 4 results in my vector. Then I'm going to calculate the sum. What is the size of each chunk? And pass the chunks one by one from start to the end. So I calculate what is the start. I calculate where is the end. Every loop will go to the next chunk. And each chunk is sent to my thread. And thread does the addition and returns everything else. You good? Huh? Yeah, so like this, and this is with thread. It's much easier with async. So threads and number of cores. Okay? With async, this is what happens. So I do the same thing over here. As you see, instead of creating a vector of threads, I'm having a series of futures over here. Simply one by one, I'm going to push back the async with the partial sum into the futures. That is up there. And one by one, I'm going to go through it, get the values, and do a total plus equal. And it's done. The difference is that over here, with thread, it's difficult because I have to send the values back and do problems. Over here, I don't need to worry about that. I don't need to have any promise in the future. Just my async is going to return the futures back into the futures, and I just go through the futures one by one, get the values out, add it to a total, and it does the work for me. Okay? So with async is much easier, and I'm glad to tell you that you don't need to do even that. Instead of doing that, all you need to do is one function call. Remember, transform reduce, the STL that you had that you could actually add stuff up with. You can add an execution policy to it. I want it done parallel. It does everything automatically. So what you're saying, I want it to be an execution policy starting data from the beginning to the end. I put the data in a vector. The initial value will be 0. LL is long, long. And then I'm going to say the process that is happening to it is plus. And this is, so essentially a lambda that returns every vector, right? Return value, increment, so, okay? And that's it. So it applies it to each element, essentially returns it, and adds them all up using plus, and puts the value and returns the value as total. Done. And because you have execution policy of parallel over there, that actually means it's going to be done in parallel. So it creates a thread for you or whatever is needed and knows what is the hardware concurrency, it knows what's the best way to run it, and runs it for you. So standard template library, if you learn how to use them, it does the parallel processing for you. You don't need to write the code anymore. Okay? It's like teaching you how to drive and say, now take the bus. Okay, or call Uber, something like that. So that's what it is. And go through the standard template libraries that we have. You have learned it before. We talked about standard template library and how it's used. You can simply apply the execution policy to whichever supports it. Like you want to do a loop through something, you can do it, and it does it for you in parallel even. Like for each that you loop through stuff, you can do that parallel. You know how quick it's going to be? Instead of having one loop or doing something repetitive, you can divide it into eight loops and get the final result at the back. It does everything automatically for you. Okay? Give me line number. Yeah, execution, parallel. So this is parallel. If we have sequential, SEQ, we have several different ones. I created a note for all these things for myself. Let me look at the note. Oh, there you go. So we have parallel execution. We have parallel and sequential. And so you use sequential for simple tasks and order matters, parallel, large data sets to do faster processing, and parallel and sequential, high-performance tasks with SIMD support. The two that we are actually following is like in the notes there are sequential and parallel. I don't think this is mentioned at all. And let me see if there's anything else I need to talk about. No, that's okay. Yeah, that's it. Any questions? Should I make these available to you guys? Huh? You want this? Okay. But this is just the note that I took from to make sure that I remember what to tell you. That's it. That's parallel processing. And yeah. All right. I'm going to stop the recording.